take it away.
Okay, good evening, everyone. It's a pleasure to see the ESC 301 students and also the folks on YouTube. It is my great pleasure today to introduce our speaker for a combined ESC 301 and Robotics Institute seminar. That is Professor Jessica Burgner-Kahrs from the University of Toronto, Mississauga, pardon me, I'm not pronouncing it properly. Jessica is an associate professor in the Department of Mathematical and Computational Sciences at UTM, also in computer science at U of T, and with a cross appointment in mechanical and industrial engineering. She's also the founding director of the Continuum Robotics Lab, which is going to be the topic of her talk today, I believe. And she moved, thankfully, to Toronto from Leibniz University in Hanover, Germany, and was also a postdoc at Vanderbilt University, I believe, with Rob, forgetting Rob's last name. Why am I forgetting his last name? Webster, Bob Webster, yes, Bob is great. Okay. Professor Burgner-Kahrs has received a number of impressive awards, including the Heinz Meyer Leibniz Prize, Lower Saxony Science Award, Young Researcher of the Year 2015 in Germany, and the Berlin Brandenburg Academy of Sciences Engineering Science Prize. She was also nominated as a Young Global Leader by the World Economic Forum. And she received her PhD in computer science from KIT, Karlsruhe Institute of Technology. And with that, since I'm not going to steal your thunder with Continuum Robots, I will hand it over to Professor Burgner-Kahrs to tell us lots of wonderful things about the Continuum. Thank you, Jessica, whenever you're ready.
Thank you so much for the kind introduction, Professor Kelly. Welcome, everyone. I hope you can see my screen. Otherwise, that would be a good time to let me know. I'm super excited to give this talk today. It's, I think, my third time that I'm speaking to the engineering, science, robotics majors, and I often enjoyed this. I usually was on campus. I think the first time that I came was this full room of students, and you were all so excited. And so I wish we could be in person today, but that's for another day. So yeah, we have to just stick with the Zoom and the YouTube. So welcome everyone, welcome all the engineering science undergraduate students, welcome everybody on YouTube. Today, I'm going to talk about continuum robots and our research in this domain. And as you may tell from greeting students, this talk is targeted to third year, fourth year undergrad students that have some fundamental knowledge in robotics, but may have not heard about continuum robots. So the question I would like to start us all off with is take a moment and think about, how does a robot look like? Think about what is that mental image that comes to your mind when I say robot. And I believe that for some of us, we may have thought about some cute robots that we saw in the movies, like WALL-E or Baymax, or maybe R2-D2 or Data from Star Trek, whatever it is that came to your mind. That would all be fictional characters. But when I asked you, I guess, what you think of a robot that is actually existing, many people would say, oh, that's probably a humanoid robot, a robot that assembles the human in terms of its appearance. It has arms and legs, can walk around, and is almost a human being. But the truth is, most of you will know from their introduction to robotics lecture that the ordinary robot today looks like this. These are serial manipulators that are used in industrial automation. Majority of those is used in industry. Welding cars, handling big parts, doing the heavy lifting, doing laser welding, spray painting, you name it. There's also parallel robots that are doing a lot of pick and place tasks these days. And then there's mobile robots. I, for myself, love my vacuum cleaning robot because it helps me big time keeping this house in a reasonable state. And there's obviously warehouse robotics, like Amazon logistics centers would probably not work with all their mobile little helpers. Then you could combine these, right? You may have seen mobile robots or autonomous vehicles with a robotic serial manipulator on them to also grab and hold on to things as the mobile robot is moving. And there may even be swimming robots that are inspired by fish or submarines that explore our oceans. And lastly, there is also surgical robotics, robots that are used in medical applications. So these are all robots that some of us may have seen as we discovered the world of robotics. Now, as a roboticist, I have mainly worked with these serial robot arms that we see on the upper left here. I've worked a little bit with these parallel robots. I think during undergrad, I have also worked with one of these little humanoid robots, also during my grad time. And then I even did my PhD on serial robot arms that did cutting of human bone with a laser. But that's also a story for another day that I'm not going to go into today. But so when I look at these robots that we see here on this slide, what comes to my mind is actually Dr. Octopus. Because when I think about how a robot should look like, I think about these octopus arms that he has, these 4 strong, durable appendages that come out of his back that are resembling an octopus. They can extend and can be used for various purposes in all different instances. So they don't have wheels like cars. They don't look like a human body. In fact, they are inspired by an octopus or a worm, a snake, an elephant trunk. And so the question then becomes, can we build small robots that have such a jointless structure? Can we build a robot of flexible, elastic, or soft materials such that this robot could perform complex bending motions and appear with these curvilinear shapes that we see by these biological counterparts here? For example, you see the snake's body being like bent into all these little curves, and it can be super agile. Or look at the giraffe. It can use its tongue to reach hard to reach places in this case. Or think of the anteater that can use his tongue to reach ants deep within certain trees, for example. That would be very useful capabilities if we had a robot that was able to do the same thing, because they could operate and navigate in confined spaces that may currently be unreachable to all these standard robots that we have seen on the previous slide. And so this is actually a field of robotics research that I devoted my, I guess, career to after I finished my PhD. And this field is called Continuum Robotics. And that's what we are working on at the Continuum Robotics Laboratory. Let us define what a continuum robot is before we move on. A continuum robot is an actuatable structure that makes it a robot, whose constitutive material forms curves with continuous tangent vectors. Continuum robots can bend, often extend and contract, and sometimes even twist along any point along their structures. So we can concatenate multiple of those individual segments to perform all sorts of motion capabilities. There exist continuum robots for inspection and maintenance tasks in industry, and also in medical and robotics. They are typically much longer than their diameter. So one dimension is much larger than the other two. And you may wonder, well, these continuum robots, how does that fall into play with the robots that you've learned about? Well, continuum robots relate to this conventional robotics when you think about a serial manipulator. Serial manipulators are usually hard-bodied robots, right? So you have rigid links and joints that are serially connected. Most of the time, they are non-redundant. You may remember that the number of degrees of freedom you need to perform a task and number of joints and stuff, there's a relationship, and then a robot becomes non-redundant or redundant. So you add more joints, you increase the degrees of freedom, and you can become a redundant serial manipulator, or have a serial manipulator with redundant properties. Usually we can think of our arm, which has redundancy in it. So I can put my hand on a point, it can position my whole arm without necessarily changing position and orientation of the fingertips. That makes a redundant property of a robot. And you could think this as to an extreme, like, for example, usually we would need 7 revolute joints in series to have a redundant robot. And you could think about, well, I could just add infinitely many of these revolute joints such that I get the link lengths much smaller. And that would bring us into the so-called hyper-redundant robotic domain, where you in fact have a quasi-continuous structure if the link length becomes short. And yet there's physics in the way, right? You cannot integrate motors and everything at such a small scale. So you can only miniaturize hyper-redundant robots to some extent. And so at some point you just reached physical limits and you may actually have no link length left. And that's when your robot becomes a continuous robot, a continuously bending structure. That's how these continuous tangent vectors are related. Many continuum robots are, in fact, also soft robots. You may have heard about soft robotics already. So we see continuum robots have some relationship to serial manipulators, as you have learned about. Now you may wonder, well, is this continuum robotics a new thing? So has this been around only since a few years, or what is it? And that's actually a super surprising fact. Continuum robots are not that much younger than the serial robot arm. It's actually almost crazy to think about this. So the same person, Dr. Scheinman, he is the inventor of the Puma robot that you have probably seen in your robotics introduction class. And he's also the inventor of the very first continuous style robot that we can see here. It's now on display in the Computer History Museum in Mountain View, California. And he did this when he was still a graduate student, I think an undergrad even at Stanford. And so he built this very short segmented robot. You have some revolute joints here in the center, and then you see these discs and these bellows that are pneumatically actuated. It's a fluidic actuator. And by changing the pressure in these bellows, you can make this device bend in 2 degrees of freedom. Still rather short. It hasn't really picked up much, but this is the first, 1965. That's only a few years later, after we saw the very first industrial robot arm. Now, there hasn't been too much happening after that in continuum robotics. On this slide, I am just showcasing some of the robots that have been developed over the past, well, I guess 3-4 decades. We see many of these continuum robots are rather big still. They resemble similar length and also sizes as many serial robotic manipulators. And we see they also have in common that we often employ some of those discs and have cables, for example, for actuation, or this pneumatic principle that we have seen also in this very first continuum robot. There's also some commercialized continuum robots even that are larger in scale. I'm showcasing the Festo Bionic Handling Assistant here on the left side, which has a payload of 3 kilograms and has 3 segments and is also fluidically actuated. And you can see it's, in terms of its motion capabilities, it pretty much resembles an elephant trunk in its motion. And you can probably identify it similar in terms of the bellows that are used. It's just a much more advanced design that's utilized here. And then there's also OC Robotics, which has built the, I guess, longest continuum robot so far. It's 5 meters long, 3 of which can be actuated. And you see that robot here. It can reach hard to reach places as it can bend up with some limited bending radii. And yet you have probably not heard about these robots yet very much. And that's because we can pretty much say in robotics, the Industrial Revolution really kicked off 1969. All these serial robot arms were introduced into the factories and have really helped with automating a lot of tasks, particularly in car manufacturing. And so these serial robot arms are usually defining what we think about as an effective robot in industry. We want a robot in industry to be repeatable, super accurate, having a high payload and significant speed, such that automation can actually bring a benefit. Now, and all of these 4 characteristics common to a serial manipulator are really not unique selling points for continuum robots. You may be able to tell just from looking at these few examples that I have shown you so far, these continuum robots are inherently compliant. So high payload is really not something they can do easily. And also because they are sometimes pneumatically actuated and that they are like flexible structures, the accuracy is also not comparable to a serial robotic arm. So the big continuum robots that are comparable in size to those have really not shown any benefits compared to these conventional robots. And there has really been not much uptake in industry of these robots. But there's a good side to this story. So continuum robots have significant benefits when you think about applications where these large scale robots cannot fly or cannot do anything meaningful. And these are, for example, in medicine. When you think about surgical robotics, which started around the 1980s, there was like the first industrial robot that they took and used it in neurosurgery to target a brain tumor. Was not like the most non-invasive approach, but with general, I guess, pathways of surgery to become more minimally invasive, to look for better patient benefit when you reduce the trauma during surgery, such that hospitalization time and recovery becomes shorter. That's when you start thinking about, well, can we reach the site that we would like to operate on, for example, within the brain, if you want to remove a tumor, or within the lungs, if you want to test, for example, take a biopsy and check for cancer. At the kidneys, you see that all on here on the slide. When you start thinking about, well, can we reach these locations with maybe opening the human body just a tiny little bit? Can we use a keyhole approach, a tiny incision, and sneak in with some instruments? Or can we even use a natural orifice like the mouth or the other route to reach some of these locations? And when you then think about instrumentation, then it becomes clear that the characteristics you have here on the slide, this hard to reach, its tortuous path, its nonlinear trajectories, and there's a lot of anatomical constraints on the way. That's when you would like a robot with dexterous motion capabilities that has the ability to really sneak through a body to do some surgery. That's where continuum robots really showcase their potential. And there are actually very many continuum robots that are used in surgery as we are speaking. For example, there are interventional continuum robots that we see here. This is a catheter steering robot, where the physician is located a little bit beside the bed, and the catheter would be entered through the femoral artery into the patient, and then it can be used, for example, to do some cardiovascular treatments. There's a similar approach that you could also use a continuum style bronchoscope to be entered through the mouth to inspect the airways and take biopsies, for example. There's laparoscopic continuum robots where you can see here is a larger port where there would be an incision around the belly button to enter the abdominal area. And then these tiny continuum robot arms could be used to, for example, resect the gallbladder or do some surgeries, for example, on the kidneys. And then there's also some continuum robots that are used through natural orifices. For example, this continuum robot serves as a pathway for surgical instruments, as it can reach the laryngeal area to, for example, do operations on the vocal folds. Or this robot here that would be used through the urethra to do prostate resection. And you may say, well, that's just a long rod, but these are continuum robots. We will see this in a little while, why these tiny little things are also continuum robots. So you notice that continuum robots are significantly smaller in diameter than the historical examples that we have been seeing. And that's really with the small form factor where continuum robots can have a big impact. Also outside of medicine, we can find many applications which are characterized by similar challenges that we have seen on that slide with the medical examples. You can see there's tortuous paths, there are constrained environments and limited accessibility in a majority of applications. For example, to facilitate in situ non-destructive inspection of tubing, pipes, and complex machinery in like aerospace, nuclear energy, oil and gas, chemical industry, you name it. You would circumvent the need for disassembly. You would circumvent these like hunched body postures that you see here. You would not need manual labor and hour-long like fiddling around with manual tools if you had robots that could do some of these tasks. Most of you are engineers, so by now you may wonder, how can we design and build a continuum robot? And that's not too easy because there are certain design challenges when you think about you want to build something that can continuously bend, and ideally you would want to be able to control this whole thing, like an elephant can control its trunk, or this earthworm can control its body. So in my lab, we investigate novel design features. We look at the design space, and this is actually pretty large. The design space to achieve continuous bending and compliance is enormous, as we found. And also in terms of design paradigms, it's quite challenging because designing robots that have no rigid elements is unfamiliar to us as engineers, because mostly we have been learning how to build robots that have rigid links and joints. And the last challenge, I guess, is the finite control problem, that you will not be able to really control all these infinite degrees of freedom along a robot body and have it really bend at any point of its length, however you desire. So the finite control, the unfamiliarity, and the large design space make this quite challenging. In our lab, we built these robots from scratch. There is no small-scale continuum robot that you could buy off the shelf. Sure, there are some of these medical continuum robots, but there are certified medical products that are meant for certain medical applications and may not serve the purpose of research. So we have to build them ourselves, which is quite a bit of fun. How do we do this? There are different things you could do. We differentiate between extrinsic and intrinsic actuation. Intuition is that you could just stick first with what works well from serial robots, right? This is what we see here, what I mentioned earlier. Use a couple of revolute joints, integrate DC motors into each of these modules, and then you have a snake robot that is quasi-continuous. It's still a discrete structure. So I wouldn't necessarily call it a continuum robot, but it's a quasi-continuum robot. You could do this with intrinsic actuation if you had the motors within the joints. Or you use an extrinsic actuation method where you still have the revolute joints, and then you, for example, route cables or wires to the back end that you could then pull and push to actuate these individual revolute joints. As these are still discrete structures, there's some limit to how small you can get them. And you can tell from some of these medical applications, the robots need to be really small, just a few millimeters. Maybe look at your pinky, and that's about the size that you would want to have at max. That's when we reach the continuous domain, really, where we usually employ different paradigms. If we look at intrinsic actuation, so actuation within the robot, we could, for example, look at fluidic elastomer actuators, where pressurization induces bending or torsion, or we could look at SMA wires for bending under temperature changes that we would integrate in some like flexible material. In my lab, we mostly do the extrinsic actuation because that is more favorable in terms of the dynamics of the robot. So we build tendon and wire-driven continuum robots and telescoping tube robots. And this is the majority of robots that are also built for the medical field. And these are the two types that I'm going to look at next in more detail with you. On this slide, you see a so-called tendon-driven continuum robot. We usually have a compliant backbone that's made of a super elastic material, for example, nitinol. And then we have these tendon routing discs that are attached to the structure. And then we pull on tendons or apply tendon tension to the back end to induce bending of these robots. Then we stack multiple of these segments, route the tendons. And you can see with that, we can achieve quite great steering capabilities. Now, this particular tendon-driven continuum robot has some great properties to it because we pioneered this design with a bachelor's student's thesis work back in 2014. He came up with this idea to have these tendon routing discs being created from permanent magnets, and they are loosely attached, only loosely floating around here, whereas the last one is attached. And so as we change the length of the segment by telescoping a tube forward and backward, we can effectively change the segment lengths. And by changing the segment lengths, we can overcome an inherent limitation in most other tendon-driven continuum robots. And that is, you can have different bending radii if you change the lengths. And with that, you can actually achieve the motion that we can see up here, which is a so-called follow the leader motion. And then just recently we found out if you also rotated that telescoping tube that defines the length of that segment, if you rotated it, the tendons would not be routed in parallel, but would be routed helically. And when you then pull on that tendon, you can see that the robot also undergoes a twist. And so you have all these motion primitives I was talking about earlier in this one segment. You may be able to stack multiple of those and reach things hard to reach. We can also use these in a parallel manipulator. This is some work we have been starting about 3 years ago, where we have been looking at making use of continuum robots, but in parallel manipulators to allow them to have eventually a higher payload and a higher accuracy while maintaining the compliance and the lightweight of the continuum robot. And this allows us to have also robots that can reconfigure. You can imagine that these robots could, for example, enter a machine for inspection from multiple locations, and then we can ad hoc reconfigure those. This is quite an exciting line of research we have been starting. And I also want to show you the smallest of all continuum robots we can build. This is this guy over here. It's a concentric tube continuum robot, where we use nickel titanium tubes. They are super elastic. Here you see 3 of those. This is the manipulator that you're seeing. On the back end, the inputs to the system is relative translation of these tubes and rotation. And then these tubes are pre-curved into a desired curvature with a heat treatment. And so then as you move them, they will conform to an equilibrium of energy. And so you can achieve this tentacle-like motion at a very small scale. You can tell when you see the hand, this robot has a diameter at its tip of 0.5 millimeters. So it's really, really small. And the inner channel could still serve, for example, an anti-factor that you put at the tip, for example, a camera, a laser fiber, something like that. We have been showing that you could use this robot, for example, to sneak up the nose and reach a tumor in the center of your brain. You may even be able to resect it without opening the brain or the skull better. And you can do all sorts of things. You could also build soft-bodied robots. I'm not going to give much details here, but you could use soft structures or origami structures. This is a particularly cool work that has been done by one of your peers, Anna, who is an Enzai student. She will graduate in the summer, and she built this origami style robot in the summer that she worked with us. That is quite exciting because it can be quite long, and it uses this origami structure and tendons on the side to achieve this motion, and it can contract to almost no length and extend quite a bit to almost a meter. Now, by now you may think, oh wow, continuum robots are really cool. But it looks like not too easy to model them. And that's right. So we will look at this question next. How can we mathematically describe continuum robots? And let's stick with what we know. So what we know from serial manipulator modeling is usually we have a robot configuration, the joint values, except we don't have joints here. So we have, for example, the relative translation and rotation of these tubes, or we may have the tendon displacement of tendon-driven continuum robots or tendon tension that we apply. So that's the input to whatever model we're building. And hopefully we may even know about external forces and moments acting on the robot. But let's neglect this for a little bit. So then we would want a model. And as we know in forward kinematics, we would like as an output, where is the anti-factor of this robot? Where's the tip of this robot? How is it positioned and oriented in 3D space? Now, in continuum robots, we also want to know, how does this whole shape of the robot look like? How does it look under external loads? How is the shape of the robot described? We use a curve. So we have a moving frame along the center line of the robot that gives us the position and orientation. And the frame, essentially 2 axes, span the material orientation at this point, And one of it, usually the z-axis, is the tangent to the curve. And then we have that moving frame that describes the whole shape. So that would be the ideal output of our model. In addition, we also obviously want the robot Jacobian relating velocities in joint space to task space. And we also want a compliance matrix to know how about the stiffness of the system. Now, obviously, this is not as straightforward to model as a serial robot arm, where you can do your Denavit-Hartenberg parameters or your product of exponentials formula and you're done. Here, what we need to think about is, well, how can we model the robot more effectively, and how can we actually make its original properties reflected in such a model? And so there are different ways that you could represent the shape of the robot and the state space, essentially, and that gives you some ideas about how you could model it. Here we see a pseudo-rigid body model where we take what we know, we approximate the robot shape as a 4-link serial manipulator, for example, such that the state space of one of those segments would just be 4 variables: phi, which is the bending plane angle, and thetas for these 3 joints that we use to approximate the shape of that segment. Another way would be to approximate the robot as a continuous shape, for example, as a series of constant curvature arcs, where we would use the arc parameters, the radius of the arc or the curvature, the bending plane angle, and the lengths to describe the segment of each of the robot's segments, for example. Yet this assumption of constant curvature only holds for some robot designs and can certainly not account for any external loads that the robot is under. So what we then usually do is a variable curvature representation, where we also in the model represent the robot as a continuous curve, where we have a base frame and then the position and orientation of any point along the robot. And as the backbone undergoes elastic deformation while experiencing small strains, the backbone is then modeled as a beam undergoing linear elastic deformation, where the stress experienced by the backbone is linearly proportional to the strain. And so the change in state can be completely specified by just keeping track of the orientation of the directors that we see here and their orientation prior to deformation. And so we can relate this through strain variables, and then we use continuum mechanics, particularly the Coursera's theory of elastic rods, to establish an explicit set of differential equations to relate actuation inputs to the shape of the robot. And then, as you may tell, the complexity of that modeling increases the better you reflect the physical phenomena that are governing the motion of these robots. Luckily, the Continuum Robotics Lab and many other researchers worldwide, we have managed to model these robots. And so you may wonder, well, how well does that work? Here I'm showing you the rule of thumb that you may want to remember. So when we look at these concentric tube continuum robot, the smallest one, and at the tendon-driven continuum robot, here we look at 2 error plots. It's histograms, which show the occurrence of the error over a set of different configurations that were tested with external loads, and the error that has been observed at the tip. Oops, sorry. You may tell that the majority of the errors is around the 1 to 2 millimeter domain, but there are also errors in more unfavorable configurations, I suppose, that are quite high or can be quite higher. And this is quite a difference to serial robot manipulators. As a rule of thumb, you could take home the error that you can have with physically and computationally reasonable model is 1.5 to 3% error with respect to the length of the robot. And that's the error you observe at the tip. Now, such a physics-based model is complex and highly nonlinear. This is about what you could get. If it's well calibrated and you neglect some physical phenomena, you can compute it in real time at several kilohertz even. What we have been starting off a couple of years back is also looking in, well, can we use data-based approaches? So can we use machine learning to eventually decrease that error? And it has been quite nice that we were able to show if you just observed the tip position and orientation of the robot. For example, here is a tendon-driven, concentric tube continuum robot. We have a sensor at the tip that measures tip orientation and tip position. And then we just jog the robot to all sorts of configurations and measure the tip. And then we have this data set, and we can train a neural network. And what we found out is that if you have a reasonable representation of your input data, you can actually get that error down of the physical model down to below 1%. So that somewhat shows you, if you were able to integrate all sorts of friction and stuff into your physics-based model, this one may also get more accurate, I suppose. We were also able to show that you could use a feed-forward neural network to model the inverse kinematics. So from a desired shape that is represented by discrete points, you can get the relative tube orientation, tube rotation, and tube translation out of that network. And at least what we were able to show is you can outperform numerical inverse kinematics in simulation for whatever that tells. This whole model inversion using deep neural networks is really exciting, also for control of continuum robots, and that's some of the things we are working on right now. In terms of control, I also want to briefly touch on control challenges that we're facing. Because when you think about a continuum robot, it's obviously a nonlinear system, right? So it's the number of kinematic degrees of freedom approaches infinity in the system. It's also an under-actuated system in that it's impossible to actuate all these degrees of freedom independently and simultaneously. And lastly, it's ill-observable, and that's the biggest challenge we're facing. It is impossible to obtain sensory information on all these degrees of freedom. So that makes it really challenging to control the full body, its shape, its contacts with the environment, and so on and so forth. So that's an active area of research where there's a lot of room for contributions. Usually what we do when we think about how do we want our continuum robot to move is that we are looking at adding some constraints of some sorts. For example, we may want to make use of some shape constraints that we want to define on the robot. We may want, as part of the robot body, for example, to not move while the remainder of the body moves. Maybe you could imagine this being within a tubular environment and it just cannot move further while the tip of the robot is in a more open environment to perform a task. You could also define null space motion for these robots as they are inherently redundant. You may want the robots to avoid obstacles, or you may want it ultimately to do follow the leader motion, as we have talked about earlier. Now, up to now, we have been mostly using sampling-based methods for planning, which comes with its own problem. So we are investigating machine learning methods on that side as well. And in terms of control, we have to differentiate where these continuum robots are used. In medicine, we overcome the majority of these challenges by just saying, well, we just do feed-forward control. We put the human in the loop because the human will magically take care of all the unmodeled effects. So we close this feed-forward controller with the user's perception. So we have a leader input device, for example, a haptic input device with which you command desired velocities that go into your controller. You use a Jacobian-based controller, for example, to compute the desired actuator velocities that you command to your robot. And then your user perceives the motion that the follower performed and will hopefully account for the error. And this works extremely well with physicians, because physicians are just amazing in looking at some sort of feedback that they get. For example, this is an X-ray of a catheter that is within the heart. And they will be able to tell, if I move this input device to the left, this catheter will move forward, backward, to the right, whatever it is. They will be able to do this matchmaking even. And it's quite remarkable. You could also think of the user looking through a surgical microscope, or they may be looking at an endoscope view. So one of the continuum robot arms or an additional endoscope would provide a view onto the tip of these robots. So this is what we usually call teleoperation, right? And that's a preferred way of operating these robots in medicine even, because it keeps the physician in full control of this robot. which is a good thing. We have also done some work on, I guess, somehow automating some of the processes in surgical concepts by using computer vision, because sometimes the vision comes for free, as we have seen. The surgeon wants, or the physician wants, that feedback anyway. So here we were looking at using visual surveying in a somewhat click and go. So you see the physician, this is a surgical microscope that they would use in brain surgery, for example. Here would be the patient and the brain would be opened and they would perform some surgery there. And then you see the Continuum Robot that is assembled onto this microscope. And that's the tiny little arm. I'm sorry, you can't see it very well because it's just this few millimeters in diameter. And so you could use that as a third hand for the physician. For example, they may want to target a specific location in the brain multiple times to test for margins as they're resecting a tumor. So maybe the robot carries an imaging probe, like a A-mode ultrasound or something, to check for some tissue properties. And so maybe the surgeon wants to just click and say, like, hey, go here, do this task, move out of the way, and I continue my manual surgery. And so we could use the computer vision here, simple 3D reconstruction of the scene. This is not brain, this is chicken breast from an experiment. And so we could use essentially the same feed-forward Jacobian-based controller, and then attach, for example, a marker at the tip of the robot to ease things up, and have the robot target, for example, these marked locations on that piece of chicken. And it was surprising to us that using this visual surveying approach, the positioning error would be below 0.2 millimeters. And you may recall this error that we saw from the modeling side was in the 1 to 2 millimeter range. So by closing the loop and having sensor feedback, you can get this down to a point where you're like, wow, this is super accurate. And physicians are actually quite excited about this. Now, this has just been preliminary work. This has just been on position, not pose. It's still work to be done, but we found this quite encouraging and exciting. Obviously, sometimes you don't have visual information about where your robot is. So if we think about beyond vision per perception, there are really not too many options because our robots are so small. We have to think about ways how to measure what we want to know and reason about their state. One thing that we usually use, and I mentioned this briefly already, is electromagnetic tracking coils. That's an electromagnetic field emitter, and that's one of these tracking coils, and it's really small and tiny, so favorable for our robot sizes. We can integrate this at certain discrete locations along the robot and sense its position and also our orientation. This is readily available in many medical settings, but it also limits us as we cannot use this in vicinity to any ferromagnetic materials, as this would cause distortion and the sensor essentially to fail. But it's a reasonably available small-scale sensors. What we're also looking at is optical fibers, where we make strain measurements along the length of a continuum robot by integrating a fiber with a couple of fiber brick gratings that can measure strain information at discrete locations, but many more locations than an electromagnetic tracking sensor could. And so we have that strain information and can probably reason about the shape of the robot, which is super useful to have better state information available. And beyond that, what we're also exploiting in control is thinking about, well, as we have all this redundancy in the system, can we exploit this redundancy to realize these shape constraints that we may have planned for? For example, here, the robot, we visualize this green sphere over here. The robot is constrained and we say up to here, the body is not supposed to move, but the tip should still follow the circular trajectory over here. Or with multiple shape constraints, as you can see here. All the green spheres are essentially the constraints we are enforcing as the robot is going. And we can realize this by having a primary task, the position control that tracks the trajectory, and having a secondary task that is realizing these shape constraints. And so we can use null space projection or weighted damped least squares to achieve the second task by resolving the redundancy in the system. And it's interesting because these are conventional approaches from serial robotics that we can then use on continuum robots and tweak them and see how well they perform, and eventually extend them towards something that makes them more favorable for our robot type. We have to put more thought into this. I just figured I'm going to show you some of these preliminary results. Now, in this talk, I mostly addressed engineering science undergrad students, obviously. And you may sit there and wonder now, should I work on continuum robotics? And obviously, my answer is yes. This is probably the coolest robot out there you could probably work on, because we are really pushing the frontiers of robotics with this type of robot. There's so many exciting questions you could answer just thinking about having a continuum robot at a small scale. There could be questions in terms of what applications could we do and testing those out, looking at how could we control them, looking at state estimation, looking at how to design a robot with certain properties. There's so many unsolved questions that a student could greatly contribute to. And as some of you will be looking around for undergraduate research theses these days, I want to give 6 topics that I could see myself supervising students with. And if they sound exciting, you know whom to email. For example, we have some projects running on motion planning and control. We would love to be able to leverage contacts with the environment purposefully and use this in motion planners. And this is usually not done in motion planning. So that's quite an exciting area. State estimation, we have that fiber Breck sensor almost ordered, so that will be in the lab soon, and using this for state estimation, using the strain and seeing where that leads us, how well we can estimate the shape of the robot is super exciting. Cooperating continuum robots, human-robot interaction, how do you design a human-robot interface that makes more sense for a continuum robot? Hybrid models that combine physics-based and learning-based models, or shape sensing and control. There's so much you could do. This is just scratching the surface. And as we are almost out of time, I want to leave you with a video that hopefully inspires you as much as it did me when we created it, about what continuum robots could do if we solved a lot of these challenges. With this, I'm going to open the floor for any questions that you may have, but I want to thank all the great, brilliant students that I'm working with, because it's really their work I presented today, and it's their collective dedication and passion for continuum robots that pushes our vision forward. And if you look closer, you may be able to identify a couple of ENSI students on that picture even. Looking forward to answer your questions. Thanks for listening.
Okay, amazing. Oh, thank you. That was great. So would you say you're scratching the surface with a continuum robot? Is that what you're saying? You did say, I was scratching the surface. It seemed like a great.
Yeah, I could just scratch the surface. I have a whole lecture on continuum robotics that goes a whole term.
Okay, so we have a couple of.
That also only scratches the surface. There could be so much more we could talk about.
Sounds like a textbook needs to be developed.
Yeah, so much work though.
Yeah. Yes. Okay. So we have a couple of really interesting questions that have been asked in the chat. One from YouTube from Yusuf. So maybe I'll ask that one on behalf of him first. For the ill observability issue, if you had, say, multiple cameras, could you observe multiple joints in the system? I think maybe he's thinking of externally, at least for position edge surveys. Yeah.
Yusuf is completely right. And it's great. We do this in the lab all the time. So we use multiple camera setups to see the robot from multiple locations and then just use computer vision to reconstruct the shape. But there's a but. Now think about where we want to use these robots. They should sneak into the human body. They should sneak into machinery. Like think of a jet engine on an airplane and it sneaks inside. You have no line of sight, so you cannot see these robots. Nevertheless, like for some of the medical applications we've been talking about, like for the catheter steering, for example, sometimes we have a thing that's called biplane fluoroscopy, where you have two simultaneously taken radiographs. And so there you have at least a stereo view on the scene, but not multiple cameras. So yes, multiple cameras would be nice if they could look through anything.
And how many, this is my own personal question, just to follow on to that, but as a question with the radiographs, how many radiographs can you take in sequence to track?
That's the issue.
Only a couple,
many of the, when you have, like, for example, a cardiovascular intervention, they do continuous fluoroscopy. That was actually motivation to do these robotically steered catheters, because it takes the physician further away from the radiation. But I guess before you die from whatever, right, you'd rather go through a radiation.
Absolutely.
It's a significant dose, but I think flying internationally is also, I think maybe similar in dosage.
Yeah, you get a good kick when you cross the Atlantic or Pacific as well. So that's very true. Okay, thank you. Sorry, I didn't mean to reject my question, but this is all fascinating stuff, so I have a bunch myself to ask. But okay, Kieran from the class asks, are there any applications where sensing along the actual continuum robot itself would be beneficial rather than just at the say the end effector, the traditional end effector portion?
Yes, most of them actually, because we would want to know what's acting on the body. But if we always only focus on the tip and as it's moving, we have no idea what's happening to the remainder of the body. It may, well, it's lightweight, right? It's flexible, so it may not really harm anything. But we may be significantly disturbed on the back, and so we would want to know where the body is. Also in terms of controlling it, right? In terms of making sure that your tip is moving in the right direction, you would need to know how is the body impacted by interactions with the environment.
Very interesting. Okay, so it sounds like tons of medical possibilities. Excellent. Lisa, thank you.
Medicine is maybe not even the worst problem, because you have a soft body, and so there's not much harm it could do. But when you think of industrial inspection tasks where you have a stiff environment, then interaction with the environment is almost inevitable. But as you want to maintain control over your tip, where it's going, you need to know what's happening all over the place. And like proprioceptive sensing is also not yet realized. One of my graduate students is actually looking with an NSI undergrad into using a torque controller, or like controlling using the motor torque to reason about things that are happening along the robot. But that's not yet ready for prime time.
Oh, very cool, very cool. We look forward to seeing that, I think, coming out in the next pub coming up sometime. Okay, one other one from Sagnik, and that is regarding error, actually in the sim to real transfer, or the sim to real gap, I guess we would call it. Performance between simulation studies and real world in terms of the robots you have now, tip error in, say, 3D space.
Yeah, that's what I had, like that was the rule of thumb. It's a 1.5 to 3% with respect to the robot's length. So you think about if the robot typical robots are like, what, 40 centimeters, you can tell it's quite some error. That is about what we can get. But then we have been seeing, right, if we used data and learn the model such that it includes unmodeled effects. In our physics-based model, we usually neglect friction because that would computation would just go through the roof. So if we didn't neglect friction, I suppose our physics-based error would also go below 1%, as we have seen in the learning-based approaches. But yeah, that's about the error we have. And it's also acceptable because you also have to see this is all open loop, right? That's just commanding these actuator values on the robot, measuring where the tip is. So as you have seen in this example where we used the stereoscopic microscope view and did the visual servoing of the tip, we got to 200 micron error. So closing the loop, including sensing and having a reasonably working well controller, we may get this error down quite a bit just by closing the loop.
Okay, I think actually you might have partially answered this already, Jessica, but from YouTube, there's a question from Spencer on YouTube. It seems like a setting such as the body is difficult because of modeling, where it's significantly more difficult basically with contact with the tissues that might even be moving. And you just mentioned model-free learning. I guess the question is, do you think that the learning techniques are promising even for situations where the body is moving, like the heart is pulsing, or you're nearby to, I don't know, something like an artery that's expanding and contracting?
Yeah, I would love to say yes, but and we have not looked in model-free learning techniques in my lab, but there has been some work by other groups, but it's always very limited. You cannot really, I guess, make sure that any eventuality is covered by what you learned. Certainly something somebody could look into, but yeah.
Cool. Okay, great. He says thanks also for that.
Thank you for the question, Spencer.
Yeah, great questions. Any other questions from the chat or from YouTube that we could? I have one of my own that I might just sneak in with. I already snuck in with one, but maybe I'll sneak in with one more. I'm going to ask about the interplay between in the human body between, say, needle steering and continuum robotics, and are there systems that use both together? I'll allow you can talk about needle steering briefly and what is involved in needle steering and whether continuum robots obviously add to that. I'm wondering about which is the combination better?
Actually, needle steering is also a needle is a low degree of freedom continuum robot, if you will. You have only two control inputs, right? Usually you rotate the needle at the back and push it in. And so it's flexible. But in needle steering, you have that additional control, which is the interaction with the tissue that kind of dictates the curvature. So usually you can have a bevel tip, and then the tissue properties will somewhat determine what curvature you can achieve. I've worked on needle steering a little bit. To me personally, it never found a compelling case. I guess as researchers, we always hoped, wow, we could steer around things and reach, I don't know, locations within the liver, but it turns out physicians can reach it anyway.
Oh, okay. So, interesting. Okay, so
I think the biggest difference is you rely on the interaction with the environment, and the same holds for catheters also, as catheters are moving through the vasculature, right? These are long limb ropes, essentially. You can only change the bending angle at the tip by just pulling on the tendon at the very back end. So you rely on interaction with the environment to steer, whereas a lot of the continuum robots I have been showing today can operate in free space, so they can hold their own weight.
So clearly much more flexible, but not just in both respects, flexible and also flexible as in having more application areas. That's very interesting, actually. I didn't realize that needle steering was no longer really being considered as a feasible way to
I think there's still work on that, but after 2 decades of research, maybe it's time to move on and think
about other
if the industry didn't pick it up yet, it may not be picked up.
Right. Okay. Very cool. Okay. I don't see any more questions. I just want to give folks one more chance. And then I will ask maybe one last one. Sorry, I have to ask one more thing. And that is the most, let's say in an industrial environment, what do you think, there's many different industrial environments, but say for small scale industrial inspection, if you had to guess, and this is a loaded question, but five or so years out, what technology do you think will be deployed in that space? Like, is it going to be the magnetic system? some kind of combination? Like what's durable enough to operate in the kind of like a jet engine or something where you have to, hard to say?
Hard to
Too difficult?
say.
I'm asking you to
It will be a
predict.
combination. It will for sure be, I think it will be a cable-driven system. That for sure. We will need to think about what would be good in terms of a sheathing that is durable enough to, interact with a jet engine, for example, without being broken. The length is still a challenge. Like long means more weight, larger influence from gravity. So everything we've learned in medical continuum robots doesn't translate well, because there we had usually shorter continuum robots, because the distances you have to overcome, for example, when you think of nose center of brain, that's like what, 20 centimeters max. When you think of jet engine and think of a huge one, that we may be talking about a meter or a meter and a half. So then, yeah, we have to think about the scaling quite a bit. Yeah, there are like borescopes that are flexible endoscopes on the industrial side that are essentially showing us, well, there are these devices that that technicians are using to inspect. They're also somewhat limp, right? So maybe that's okay. Maybe it's just making use of the environment as we're going. And then that loops back to, we need to be able to sense the shape and know what we're doing, because then we can utilize interaction with the environment to reach places that we couldn't reach.
That's fascinating. I guess you could use that, like you could almost push off of, or just plan to rest on certain points to support the weight of the robot itself while you move, as you slid. Wow, fascinating stuff.
That's somewhat contradicting in robotics, right? Because mostly we want to avoid contact with the environment to any cost.
Yes.
And
I was thinking in my group, we spent all our time thinking about how not to hit anything ever.
Yeah, now it's like, no, let's hit things, let's make use of it.
Just one thing you touch very gently, only, ever, never anything else, ever. Very interesting. So this is it's counterintuitive, as you said, to the way we normally operate, literally in the field of robotics. Okay, I'll have one last one from the chat, and then we'll close off for today. Thank you so much to our wonderful speaker. Vishal from the YouTube channel chat says, this is a great last question. The parallel continuum robots that you showed are something very new that I hadn't seen before myself. What are some possible applications of those robots?
Could be multiple things. One is inspection, where you need, or like maintenance repair, where you can enter machinery from multiple locations, and you couple these robots to a parallel structure to gain on the accuracy and repeatability, hopefully, and payload. And then you disassemble them and they move out of the system. And you could see this collaborating continuum robots in very many applications. This was just I guess, broad example, but I could see a lot of merit of this if we got it to work. So maybe Vishal can help.
Yes, absolutely. Okay. All right. Well, we're just a little bit past the hour of 6, so 6:15. So we'll close off here, but let's thank our speaker, Professor Burgner-Kahrs again. Wonderful talk. That's a super amazing, fascinating stuff. And the talk was also fantastic. Thank you. I have to ask you more about the video at the end after the talk is over. For those of you in the class, please remember that we'll have another seminar coming up during the, I think it's this, I have to check the date, but early March, we have a second seminar, which, our next seminar coming up, which is Jeff Delone from NASA JPL, actually will be speaking.